Okay, now that we know a little bit about torque, we're going to look at rotational form of Newton's second law versus what we're going to refer to as the old translational way. Basically, translational motion has been everything we've studied up just about up to when we started talking about these angular quantities in chapter 9. Like when we learned Newton's second law, for instance, F equals ma. These are all linear quantities, linear accelerations. So translational motion pretty much just means, simply put, that if I put a force or a net force on an object, I will accelerate that object's mass in some linear direction. Well, basically, now that we got a little bit of knowledge about rotation, there's a rotational form of Newton's second law. So it just kind of falls in place. It's the same idea, just as kind of reported through the concept of angular quantities. So instead of the sum of all forces, remember what it takes to rotate an object, not just push it linearly, but to rotate something about a pivot point is not just a force, it's a torque. So instead of saying sum of all forces, we're going to say sum of all torques. This is just going to be Newton's second law as applied to rotation. And instead of mass, remember when you rotate an object, the ease or difficulty it is to rotate an object or change its rotation if it's already rotating is not just due to mass, but it's mass and mass distribution. And we called it that moment of inertia, and it is I. Now this formula is specifically for the rotation of a rigid body, which means an object which is not going to change form while we're rotating it. If form changed, that would be a little bit more difficult because the moment of inertia would constantly be changing due to mass distribution. So we're going to work these just assuming what we're rotating is going to stay a rigid body and not change mass distribution. Therefore, I will remain the same. And instead of taking it times a linear acceleration, we will take it times alpha, the angular acceleration. So this is just as powerful in the rotational form as it is in the translational form or linear form we had earlier. But this is just Newton's second law. This is F equals ma for rotation, but now it's torque equals I alpha. Now, just like way back when we looked at this seems like a small little equation, but it could explode into a much bigger problem because this is the sum of all torques, like this is the sum of all forces. There might be only one torque, there might be 5 torques, and we have to total them all up on this side. So, and we'll have specific formulas for moments of inertia, and we could replace alpha with a lot of formulas we learned back in chapter 9. This by no means is a complete version of all the ways you could arrange this formula, but as an example, let's just quickly note what we could plug in here in some circumstances. All right, let's keep it kind of simple, and let's say we just have a single torque. The sum of all forces, we're going to rotate an object, and the torque, there's just going to be one. And that torque, remember, could be replaced with Fr sine theta for the magnitude of it. So that could easily turn to that. We could be rotating an object such as a disk. And if you recall from chapter 9, the moment of inertia of a disk is 1/2 mr squared. And one way to figure out alpha, angular acceleration, is by definition the change in angular velocity over time. So we could say omega minus omega initial over t. So although small and condensed in this form, it could turn into a lot of variables involved. So this is just one way we could substitute some stuff in. There's obviously the formula for I could differ, the formula for alpha could differ, but these are just, this is a common thing we have to do is plug in some of these old formulas from prior sections and prior chapters, and there also could be more than one torque involved on this side to sum up. So we'll soon be jumping into applying this into some example problems, some being easier, some being blowing up into much larger pieces.